today I want to talk about some conjectures beyond unreward, beyond length sorted conjecture. We'll be talking about still in the context of just chloride. And so these have to do with atypical varieties, typical subvarieties. So what's an atypical variety? Well, so take V, be some closed subvariety inside C star at the end. So far we'll be dealing with just when does V contain a torsion point. Because if V is of dimension less than n, it doesn't contain most points, so given a random torsion point, you expect it not to contain. But now we're going to deal with something a little more general. So take T inside C star of Vn, a torsion coset. Now, you expect, what do you expect? Well, you expect that the dimension of T plus the dimension of V is less than n, then T and V don't intersect. Okay, so we're very naive. More generally, so we get this right, we expect that the dimension of the intersection is at most, or we expected this to be equal to the maximum of 0 and dimension of V plus dimension T minus n. That sort of naive dimension theory tells you that if V and T are sort of random varieties and they intersect in a subvariety of this dimension. Okay? Okay, so whenever this doesn't happen, whenever the dimension intersection exceeds this quantity, we say we're dealing with an anomalous subvariety, atypical subvariety. Sometimes called anomalous. So if non-empty and is bigger than this intersection, then we say that V intersect T is atypical with respect to V. So, as like the simplest example, keep in mind, just to keep during this point, if V contains a torsion point, then you can take T to be that torsion point, and this here will be violated, because you have 0 is bigger than the dimension of V plus 0 minus n, because V is proper. This includes the special case, all the torsion points inside V. Okay. All right. So, to give a more precise definition, if W is inside V is an irreducible subvariety, then we say W is atypical. If there exists some torsion coset T, with W containing T and dimension W bigger than this thing up here. Okay, so we can actually make this a little more precise. We can sort of say how atypical W is, and it sort of gets more atypical the more this is bigger than this. So we can define the defect of W with respect to V delta set V of W. This is defined in sort of different but equivalent ways throughout the literature. I'll define it like this. So it's the supremum over all torsion cosets T, which contain W of this quantity. Okay? We just, I think I did it correctly. This side minus this side. So in particular, W is atypical if its defect is positive. Any questions about this definitions? All right. Let me just right off the bat write down the main conjecture in this field. This conjecture is due independently to Zilber, who arrived at it from sort of logic considerations, which we might say something about later in this course, and Bombieri, Nasser, and Zani. Who arrived at it from considerations of heights. And it does the following. Well, so you don't expect atypical intersections, that's why they're called atypical. But they're in some sense unavoidable, right? I mean, you could, for example, imagine a torsion coset. So you can do the following thing. Let me write it down here. You can take some torsion coset T inside C star Vn. Let's say of dimension n minus 1. This is all an example. Could take some like W inside T, some random W of dimension n minus 2, and then you can take some V containing W of dimension n minus 1. You can sort of do all these things, they're really easy to do. And lo and behold, you produced inside V, which is just some random variety a priori, like it has no special multiplicative structure, but it has this, oh, did I screw up? Sorry, these numbers are totally wrong. What I mean is, I want this to be like n minus 2, n minus 3, n minus 9. Okay. So you can do all, you can make these numbers whatever you want. But the point is, with this choice of numbers, all of a sudden W is atypical inside V. This intersection of V with this guy, which is codimension 2, is only codimension 1. So these varieties, varieties in general will have atypical intersections, just like varieties at torsion points before. The idea is they shouldn't occur too often. There should be some structure to how these guys show up. So let me give a conjecture, then I'll state 3 different equivalent ways of saying it. So the first one is very simple. It says that, so for V inside C star to the n, there are only finitely many maximal atypical varieties in V. Okay?
So atypical implies irreducible?
Yeah, let's just stick with the definition there. It's irreducible. Yeah, I guess when I wrote here, I could have said a connected component, I think per se. But yeah, we'll go with the definition. So, an equivalent way of saying this is not one of the 3 equivalent ones, but So just like for length conjecture, what is it saying? Well, it's saying if you take all atypical varieties under containment, there's only finitely many maximal elements. So equivalently, the union of all atypical varieties in V is Zariski closed. It's already a subvariety. You just union up all atypical varieties. All right. So a little progress is made towards this, but on the whole, it's still a very, very open conjecture. So let me give just a couple of examples, maybe somewhat concrete examples of what this statement is saying. Example 1. So this one is the simplest example. So take V inside a torus of dimension 3 to be an irreducible curve. Which is not contained in a proper torsion coset. Okay. Well, so what does it mean to say V is not contained in a proper torsion coset? It basically means that V itself is not atypical. Okay. So since V is not atypical, and V is a curve, the only subvarieties in V are points, and so the conjecture, which I'll call V of Z, so V of Z implies that V has finitely many atypical points. Okay? And so what is that saying? Well, certainly it implies that V has finitely many torsion points. We already know that in length conjecture. But more specifically, it implies that for all but finitely many one-dimensional torsion cosets, T inside C star cubed, V intersect T, well, so it's not quite empty because you might have a torsion point, and that torsion point lies in many of these. So if you replace V with VO, some proper Zariski open, some Zariski open set inside T known, so V minus finitely many points, then that intersect T is empty. Okay, so let's say it now in a different way. So what does it mean for a point to be atypical? Well, it means there's a one-dimensional torus coset, a torsion coset, which contains that point. And so what's a one-dimensional torsion coset inside C star cubed? Well, it means to satisfy not one, but two multiplicative relations. Okay? In other words, if you look at a multiplicative group generated by the three coordinates of your point, it should be one-dimensional. So, another way to say it is that for almost all, so all but finitely many, x, y, z, complex points of V, if you look at the multiplicative subgroup generated by x, y, z, so this thing, which is the set of x to the n, y to the n, z to k, where m and k are integers. This is our free abelian group, and we're saying for all the finite many points, this has rank at least 2. Okay, because if it's got rank 1, that means you have 2 separate multiplicative relations that define the torsion concept, and so make it equal. So now let's give a concrete example. So specifically, we can look at V is the subvariety defined by x plus 1 equals y, x plus 2 equals z. So in other words, it's the set of all triples of points x, x plus 1, x plus 2. In other words, c star cubed, so I guess we don't want x to be 0, 1, or minus 2. So V is this like regular line inside a three-dimensional torus. Now this is not contained in any proper torsion coset, because if you multiply any power of x, x plus 1, and x plus 2, you don't get a constant polynomial. Okay, so V is not contained in a proper torsion coset. So what is this statement saying? Well, in particular, it implies some struggling a little bit in particular, it implies that there are finitely many let's say rational numbers q such that q plus 1 and q plus 2 are inside the multiplicative group generated by 2, 3, 5, and 7. Okay? Sorry. No. It's inside the multiplicative group generated by 2. What I want to say. Okay, a week mistake. By 2 and the roots of u. Okay? So, Lang's conjecture tells us that we already know that there's finitely many points where x, x plus 1, and x plus 2 are roots of unity. That's sort of easy in this case by committing considerations. But sort of the strength of it that if you throw in any other random number, just 2, there's finitely many points for this is true. And this is already like a very concrete arithmetic statement, right? Apart from anything about torn varieties or things like that. In fact, it's still true if you throw in finitely many other primes, but it's a bit hard to do, so we'll do that later. Right, questions about this?
So can you say anything, is anything unconditional?
Yes, in fact, this case, when V is a curve, it's not. We'll talk about that in a bit. As far as I know, only the curved case is known, but I'm not 100% cut off in literature. Okay. Before I go to a second example, let me point out that, so for Lang's conjecture, we reduce to Q bar sort of right away. Right is that we're not defined, or Q bar, we're not interesting, because all our torsion points will be defined with Q bar. In this case, that's no longer true. Okay, so you could easily have a variety which is not defined with algebraic numbers, but defined with the complex numbers, and there's no reason for it a priori not to intersect infinitely many one-dimensional torsion coefficients. So, in fact, there are some arguments which get bad from CDQ bar sometimes, but there's going to be more complicated. All right. That's one example. Okay. Let's go to a second example. So suppose again we're in C star cubed, so V is in C star cubed, so not atypical, not contained in proper torsion coset, and the dimension V is 1. Then you can ask the following symmetric question, so you can consider points in V intersect n times V for n a positive integer. Okay? So you can look at the variety V. You can look at the variety n times V, so we're inside C star of the n, so we're looking at sort of the nth powers of all points in V. That's some variety as well. I'm wondering how many points are inside V intersect n times V. Consider, Jesus. Okay. Okay, so then B of Z, we'll show in a second, implies that the union over all n, at least 1, of V intersect n times V is finite.
Did you say V was an abelian variety, or is n times V a diagonal?
I always write V to the n, but that sort of means the product thing. Here, so what by n times V? I mean the set x to the n, y to the n, z to the n, where x, y, z is in V. Just like last time we used 1 over n times V or now. You can also use 1 over n times V. Yes, sorry. So what this to be finite, I want to restrict it. Okay. So note first of all, as far as I know, the statement is open. I need to prove it. That's cool. I don't know how to prove it. Maybe someone else does it. I don't personally. So one thing I want to point out is that the assumption that V is atypical here is necessary. So suppose that V is contained in a two-dimensional torus coset. Like let's say V was actually inside C star squared. Well, then n times V would be a curve in that same coset. Now you have two curves inside a surface, and two curves on a surface you would expect to intersect. And the intersection points most likely are going to be different, and they would be the same. And so now you really would expect infinitely many intersection points. Alright? So yeah, this assumption is really sort of the correct assumption to make. Okay, let me explain why B of Z implies this. So consider V cross V, and this is now a surface which is sitting inside a 6-dimensional Z star. Okay, so I just made like pairs. First three are in the first V, the second three are in the second V. Now, note that this surface is very much atypical. It lies inside a 3-dimensional torus coset, namely the diagonal. x1 equals x4, x2 equals x5, x3 equals x6. Okay? So sort of how to say, the defect of V cross V inside V cross V is, sorry, I'm saying nonsense, 1 second. No, I'm saying nonsense. Because V is not a different. Okay. So ignore the first 3 sentences. So because V is not contained in any proper coordinates. Okay. Okay, so now suppose you have x, y, z is in V, and x to the n, y to the n, z to the n is in V. Okay. So what does this mean? So then, if you look at the point x, y, z, x, y, z, well, this is a subvariety inside of V cross V. It's a point. Moreover, this thing here lies inside a sorry, I mean, do this, okay, do this. Oh, I made that incorrectly. Sorry, I may boycott this example maybe for next time.
That 3-dimensional, and then V cross V is 2-dimensional, and you just kind of
Sorry?
that thing is that lies on a 3-dimensional surface, right? Because there's 3 equations, just cut it out.
Yeah.
And then V cross V is 2-dimensional, and you have anything missing a dimension.
Ah, yes, okay, good, thank you. Yes. Okay, so this thing satisfies, yes, okay. This thing satisfies 3 equations. Right, V equals V is a surface, and so this is inside V equals V, the 3-dimensional torus, and so it's atypical. Equations, 3 multiplicative equations, so it's atypical. Okay? That's it? Okay. Then what do we learn? So if this union is infinite, if union V intersect n V is infinite, then we get infinitely many points like these, and so these must lie inside some atypical curve inside V. Let's call this point P sub n. Then sort of all with finitely many P sub n lie in an atypical curve W inside V cross V. Okay? Okay, so now, so W is atypical. So since W is atypical, you guys don't want to finish the argument because I've confused already. Okay, so I don't want to give the fun part of the argument. But so, okay, I won't give the fun part of the argument because I think I've messed something up. Anyways, there are atypical curves W and V cross V. In particular, the diagonal V inside V cross V is atypical. It satisfies three multiplicative relations, which you don't expect. But you can show that since these points vary, you can rule out a whole bunch of multiplicative relations. So you can show there's no curve containing all of these points. It's not hard, but I'm confused. So I'm not finished the argument. Maybe I'll finish it next time and figure out what's going on. All right, just to recap. Sorry, I fumbled this a little bit. The basic idea, though, is if you have intersections V with NV, and you look at the surface, and these intersections correspond to typical points on the surface. Then you apply the BMC conjecture, and it gives you an atypical curve. And now you've gone from sort of an arithmetic question to a question of sort of algebraic geometry. It's much easier to study.
So, a point is atypical assuming it satisfies one multiplicative relation?
Not in general. So if a point is on a hypersurface, say, then multiplicative relation is not enough to make it atypical. 2 is enough to make it atypical. So see, the point is that it's a question of codimension, right? So V cross V is dimension 2 inside here. This point satisfies 3 multiplicative relations. So it lies inside a torsion coset of dimension 3. And 3 plus 2 is less than 6.
Yeah.
And
So it's an atypical point on V cross V.
Exactly. Because given a random 3-dimensional variety, you would not expect it to intersect this 2-dimensional variety inside the 6-dimensional space. That makes sense?
Yeah.
Cool. Okay, yeah, so let me get back to this next time. All right. Yes.
Yeah, so here, you're using the conjecture here, right?
Yes.
That is in the same one? Yeah.
Yes.
Okay.
This step here is exactly what that conjecture is using. So yeah, this is, as far as I know, still open because V cross V is the surface. Surfaces, as far as I know. You don't know the BMC conjecture. Okay. So let me give another form of the conjecture. So this is called this is formulated by Jonathan Vila. He calls this the articulated BMZ conjecture. So it's a priori slightly stronger form, but we'll show they're actually equivalent. Remember, we had this notion of defect, where you don't just keep track of whether it's unlikely, but how unlikely it is. So he says the following: for delta, a positive integer bigger than 0, write a delta of v to be the set of irreducible subvarieties of defect at least delta. So if delta is equal to 1, this is precisely the atypical subvarieties, and then as delta goes up, you get sort of, you restrict to more and more atypical looking guys. So the conjecture is that if you look at this, then this has finitely many maximal elements. Again, equivalently, the union of all the atypical varieties of defect at least delta is a proper substrate. Okay? In theory, you could also restrict the delta less than 0, but that's sort of boring because as soon as delta is 0 or less, V becomes the set, and then V is the only maximal element. That's kind of uninteresting. Okay, so again, this sort of implies the BMC conjecture immediately, just by taking delta is equal to 1. And we'll prove that even though it looks stronger, it's in fact of the same strength. So BMZ implies articulated beauty. Okay? Okay, let's prove this. So we'll proceed by induction on dimension. Okay, so suppose that V is MC star to the M, and then without loss generality, we can assume that V does not contain in a proper torsion coset. Because if V is contained in a proper torsion coset, we can just look inside the proper torsion coset. And everything remains the same, except for all our defects go up by 1. So assume V is not contained in the proper torsion coset. Okay, and by BMC, we're assuming A1 of V, that's what I call it, right? A1 of V is finitely many maximal elements W1, let's say to Wm, which are inside V, but are not equal to V, because V is not atypical by assumption. Okay? Okay, now delta is bigger than 0, so any subvariety of of V, which is has defect delta, has defect in particular at least 1, so it must be atypical. So it must lie inside one of these Wi's. If WV is atypical, W is inside WI for some. Alright, but if W is inside WI, then the defect inside Wi of W, if you look at this, well, it got the same expression as for V, only you're subtracting dimension Wi instead of dimension V. And so this gives identity. It's the defect of Wi inside W, so some constant number for the defect of V inside W. The defect of W inside V. Yeah, I think I misspoke. The defect of W inside Wi is the defect of W inside V, just plus a little bit more. So in particular, asking that this is bigger than or equal to delta is exactly equal to asking that this is bigger than or equal to delta plus this one. Okay, so therefore, what we get is that A delta V is the union that goes from 1 to M of A delta plus dV minus V delta I of W. Now by induction, this is finding many maximum elements, and so we're done. So what's sort of happening in this proof is, being atypical defect, at least delta, means you're at least atypical. So you're contained inside the finitely many maximal atypical guys. Now, being contained inside these already gives you some amount of defect. So you're sort of already inside a smaller than expected torsical set, because they're typical to begin with. And then you sort of want to make up the rest of the defect inside those guys. Do this induction procedure where you sort of gain some amount of specialty every time. That's sort of intuitively what's happening. Okay? All right, so let me give one more definition, one more equivalent way to think of this. So, final definition. We have a variety V, again, C star to the n. We say A and V is optimal. Again, this notation is due to John Pila. If we sort of can't find anything bigger than A without decreasing its defect. So if you take anything bigger than A, you make it less special. So if for any variety B irreducible, which contains A and is actually bigger than A, the defect of B is actually less than the defect of A. Okay? Okay, so then we can just talk in terms of these optimal varieties. So it turns out that B and Z conjecture is equivalent to B has finitely many optimal varieties. So optimal varieties are kind of nice to work with because you don't have to worry about under-inclusion or anything like that. Just have finitely many optimal varieties, period. They make many arguments very key. Okay? Let me kind of quickly go through the proof, and then we'll finish. So first assume that the set of optimal varieties of V is finite. Okay? Now, if A and V is atypical, so what does that mean? That exactly means that delta V of A is bigger than 0, so they get positive defect. So we follow from definition pretty quickly that if A is not optimal, we can keep increasing it until we land inside some optimal guy with defect, at least the defect of A. So then A lies inside B with the defect of B, at least the defect of A, and be optimal. Now the defect of A is positive, which means the defect of B is positive, which means that B is unlikely. Therefore, B is atypical. This means that every atypical variety is contained inside an optimal variety, which is atypical. And so we're done. So the maximal atypical varieties are optimal. So we're done because we're assuming there's only finitely many optimal varieties. All right, so going the other way now, assume B and Z. So then V is a union of guys inside here, with a WI being maximal atypical. Okay, so now, if you have a variety B inside V, which is optimal, and B is not equal to V, because V is always optimal by our definition. There's nothing bigger than V, so the condition is empty. But if B is not V is optimal, that means we can't increase B to V without dropping the defect. So the defect of B is bigger than the defect of V, which is 0. And so B is atypical. So B is inside WI for some I. So by assumption, these are the maximal atypical guys. And so we learn that the optimal varieties of V are just V together with the optimal varieties of WI. And so we're done by induction on dimensional varieties. Now we're done by induction. Okay. Any questions? Yes?
Is maximal atypical equivalent to optimal? Or does it follow from the proof?
Is maximal atypical equivalent to optimal? I'm really bad at these things, to be honest.
That's okay.
I think not. So not, but for silly reasons. Like basically yes.
Okay.
But for example, V is optimal always, but V is rarely atypical. So the only counterexamples are that and things like that show up from the induction step of the proof, which I can't quite figure out quite what they are. But they're very close to each other. Alright, so next time I'll fix the thing that I screwed up, and we'll talk a little bit about the proof of this in the curve case.